Welcome all. And before starting with the talk today, I would like to share a small story from my end of why I even thought of giving a talk on this topic in the first place. So, uh, in the earlier this year, I was working on this project on credit risk assessment, and I was not able to get the required accuracy, basically something that I was expecting, even after using different ML models like logistic regression, decision trees. And at that point of time, I just kept my research on so that I can find some ML model that can actually lead me up to the accuracy that I have been looking for. And that's when I stumbled upon a concept known as ensemble learning. And that's what we are going to talk about today, beyond single models, the secret sauce of predictive success. So here's a little intro about me. Hello everyone, I am Yashasvi Mishra. I am currently working as a data engineer at AB InBev, and I have a good background in machine learning and research, thanks to college projects. Um, so I have been very passionate about technology from the start, and I love engaging in open tech communities. That's how I became a part of PyCon back in 2020. And apart from that, I am a diversity advocate, and I have contributed to a number of diversity and inclusion initiatives by being part of communities like PyLadies, which is again a part of PyCon, my starting point in PyCon actually, Women Who Code, and Women in AI. I am a problem solver at heart. I really love to engage in new challenges, as they not only give me a chance to explore and learn, but they also give me a chance to deepen my concepts in that particular area. So, before getting started, let's take a look at the agenda today. So, first we'll be having a look at the basic concepts that lead us to ensemble learning, the concept of wisdom of crowd, and weak and strong learners, followed by a detailed discussion in ensemble learning and exploring its different types, bagging and boosting, stacking and voting, followed by a comparison, a collective comparison of all the techniques that we would be discussing today. So, before I get started, a question to all of you. Why do you think that whenever we are electing a leader for a country or a state or even for a community, there's voting? Any answers? Yeah. But why democratic? I mean, what would be the reason behind it? Exactly. Yeah. So, our next concept here, like a fun fact, most of the things in machine learning are very much related to real life scenarios, like this concept right here. Wisdom of crowd states that a single person knows very much less as compared to a group of people would know. So, whenever we are electing a leader for a community or a state or a country, we tend to have voting as a process. So, we take into account the opinion of a number of people rather than taking into account the opinion of only one person who might be biased towards a single candidate who are basically standing for being a leader. So, similarly, in machine learning, in the wisdom of crowd concept, we leverage the collective power, the collective intelligence of machine learning models, and finally get a reliable output. And that's what happens in ensemble learning. Let's quickly get on to the next concept to understand this much better. Weak and strong learners. Now, weak learners are the machine learning models who tend to perform slightly better than random guessing. Now, why does this happen? No? So, the reason is that when this ML model is training on the training data set, it is not able to capture the underlying data patterns very well. And that's why when it is exposed to a new data set or the testing data set in much simpler terms, um, it tends to perform very poorly. And that's when the strong learners come into picture. They train on the training data set so well, they capture the data patterns in a manner that when exposed to a new data set, they tend to perform in a very nice manner and give us the output or the accuracy that we have been looking forward to. So you can see here in the picture, a number of weak learners form a strong learner, which takes us back to the example that we just saw in the wisdom of crowd, right? One single person is a weak learner, and a number of people all together, the crowd, is a strong learner. So there's one more thing here, that weak machine learning models tend to have low bias and a high variance, whereas the strong learners have low bias and low variance. So just to understand what I exactly mean by bias and variance here, so bias in very simpler terms is the error in training data, and variance is the error in testing data. Now, right here in the graph that we see, the model complexity versus error rate. Now you can see here that when the model complexity is very less, I tend to have a higher error rate. Why does this, like, what exactly do we mean by this, right? So this means that the less complex my model is, the less data pattern, the less detailing in the capturing of the data pattern would be happening here. And hence, it would not be performing well on the training data itself. There would be more error in the training data. Now, after understanding this, this should be right, right? Like if I increase, like if the model complexity is at its best, then there shouldn't be any error. But this is not what we are seeing here. We see that even when the model is at its most complex, we do have an error. The graph goes up. Now, in that scenario, what is happening, that the model is capturing the noise of the data as well. Basically, it's getting distracted by the features that it should not be focusing upon. So that is the case where we have high error in the testing data, high variance. The terms here, underfitting, is nothing but high bias and high variance. That means high error in the training data as well as high error in the testing data. Whereas overfitting is low bias and high variance, means low error in the training data and high error in the testing data. So this was it about the bias and the variance terminologies. Coming to the main topic of our talk today, the ensemble learning, which is very much like, we just have the definition here, that it is basically combining multiple models to get a generalized prediction, and it improves the performance of the model that we have. The major pros of the ensemble learning technique is that we tend to have a better predictive performance, better accuracy, and more robustness in the output that we have. Like, we get a more reliable output that we would be getting if there's only a single model which is performed. Let's have a look at its different types. So here are the different types of ensemble learning. Bagging, which is the same model being trained on the different subsets of our data. Boosting, wherein the model is trained in a sequential manner every time correcting its previous mistakes. Stacking, wherein we combine the ML models in a stacked manner to get the reliable output that we are looking forward to. And finally, voting, which basically combines the predictions of multiple ML models and does a majority voting on the output that we get from each one of them and finally get our output. So let's dive deeper in each one of them. So our first technique for the day, bagging. Now here, let's jump into the picture that we see here. We can see that we have a data set and it is bifurcated into a number of subsets. And we have a single model whose different versions are doing a prediction on each of the subset. This particular technique is known as bootstrapping. And as we would be getting a prediction from each of the subsets, right? What we do is that we aggregate all of these predictions together to get a final prediction. So bagging is at times also known as bootstrap aggregation, as we can see here. Now, a lot of times what happens is if we are taking the case of classifier as we have in the picture, while aggregating there's a voting that happens. However, in case of a regression model, like had there been multiple versions of the same regression model, there would have been averaging out of the output and then the final output would have been given. So now let's have a look like how does the original data set bifurcate into different subsets. This technique is known as sampling. So let's understand sampling as it is done both on row and column level. So data set is divided both on the row as well as on the column level. Now you can see that we have a data set which has 6 features, 1 target variable and 5 rows. Now what happens here is that we have the 2 subsets that we are creating, right? So if we only talk about row sampling, that is dividing the data only on the basis of the different rows, we see here that any random 4 rows are picked up and then they are fed into each of the subsets. Now in the upcoming slides, we would be encountering terms like row sampling with replacement, row sampling without replacement. Now what does the replacement term means here, right? Replacement means replication. So what happens here is, if it is said that I am bifurcating the main data set into subsets with row sampling with replacement, it means that I will be like row number 1, right? We have it here. It is in subset 1 as well as in subset 2. So if the replacement is there, then I can have this row in the n number of subsets. How many of them I create, I can have the same row if I want to have it. However, if it states without replacement, I am not going to have the row here. If I use row number 1 in subset 1, it's done for it. I'm not going to use it in any other subset, no matter how many subsets I'm going to create. Same happens for column sampling. In column samplings, we have randomly picked up 3 columns, 3 features in each of the subsets. And same is the case for column sampling with replacement and without replacement. Like, I do not have an example right here for column sampling with replacement, but yeah. So coming to the main point, that the subset creation that is done here finally is done with the help of row as well as column sampling. So here's a small illustration showcasing how does bagging work. You can see that it is being bifurcated into different sets, and then there's a training that is happening, and there's a final aggregation for all those predictions. So here are just different types of the bagging. So I've attached the code samples for your reference. Now, bagging also has 4 types. First being bagging itself. Here what happens is that we will be bifurcating the subsets of the data using row sampling with replacement. However, in pasting, what would be happening is row sampling without replacement, just as we saw before. So the data sets that we had, like the subsets that we had created, it's row sampling with replacement. So yeah, bagging would fit there, but not pasting. Coming to the other 3 random subspaces and random patches. Now, in random subspaces, what happens is that here column sampling is happening. So basically, we are bifurcating the data only on the basis of columns. And in random patches, what is happening is that we are bifurcating the data based on columns as well as rows. So the last example that we saw would most precisely fit for random patches. Now coming to the second technique, boosting. Now, as I said before, a lot of scenarios are based on the real lives, and this is exactly one case. Like, we should learn from our previous experiences and not repeat our mistakes, correct our faults, which we do not do a lot of times, but we can rely on this model. It always does. So, what happens here is that the original data set is taken all together, like there's no bifurcation as such that is done on it, and my classifier model will directly perform it. And then on the different data points, on some of the data points it will perform correctly, while on the other data points it would be faltering. It will not perform very well. So the data points where it does not perform very well are weighted, and it is again like a new data set is created, wherein the data points where the performance of the ML model was not that well is weighted more, so that when I again train my classifier on it, it is bound to focus on the fault areas and correct it. Now, this particular process will be taking place for the number of iterations I define for it, and that's how it is finally going to give me the prediction after correcting its fault over the different iterations. So here's one small illustration for the same. Just a second. Yeah. So the data set is created, training sets, each time it takes a feedback, then again creates a data set, again the training is done, feedback, and then again, and then that's how we actually get the final result. Coming to the next technique. Yeah, sorry. Before that, let's have an example. So XGBoost classifier, I think we all have mostly heard of it. So that's the example of the boosting technique that we have from the ensemble learning. And here's one code sample that I've attached for the same, wherein we do not have much difference between the training and the testing accuracy, showcasing that in the training itself, the data patterns were captured so well that there wasn't much error in the final testing that was done. Coming to the next technique, that is stacking ensembles. Now, stacking is like, as the name suggests, very well suggests that the models are going to be stacked upon one another. Now, what exactly is happening here? We can see that we have a training set, and model 1, model 2, and model 3. Each one of them are parallelly training on the same training data set and are finally giving their output. Those outputs are fed into a new training set, and then we have a meta model which trains on the new training data set that is formed, and then it gives a final prediction. So here we can see that the meta model is stacked upon the initial 3 models that we had that were being trained on the initial data set, and hence give us a final prediction. So let's understand it better with this particular image. So here what's happening, as we can see, from model 1, 2, and 3, we have the prediction column along with the target column. And on this particular new training data set, our meta model will be training, and after that it would be giving, basically being tested on the new testing data set which is formed, and then it would be giving us the final prediction that we're looking forward to. So here's one code sample for the same. Here is what, like the initial models that we were using, right? Model 1, 2, and 3. Here I've taken only 2. random forest classifier and decision tree classifiers. And after that, what is happening is the meta model that is being used to being stacked upon these two models' prediction is logistic regression. And after that, the final prediction that we get is on the 87.35 percentage. It also did well, like there wasn't much difference between the training and the testing accuracy. Hence, we can state like there wasn't a lot of bias or variance that we see normally. Coming to the last technique of today, voting ensembles. So even here we use multiple ML models. Like it's not just one single ML model as it was the case for bagging and boosting. It's multiple ML models that are being used here. Each one of them would give an output. Model 1, Model 2 and Model 3. Model 1 gives an output of 1. Model 2 gives an output of 0. And Model 3 gives an output of 1. A voting is done and we get the final output as 1. So in classification models like logistic regression, SVM, random forest, um, we in the case of classification, there's like a voting is done and we finally get an output. However, in case of regression predictions, um, it is not possible to have like a voting, a hard voting to be done here. So what happens is that we average out the results. So here's one small illustration. With the MRI scan, I go to 3 different doctors. 2 of them say no, 1 of them says yes. I'm safe, I do not have a tumor. Same is the case with ensemble learning model that we have. The MRI scan data is fed into it. 2 of them say no, 1 says yes. So the maximum vote goes to no tumor, and that's the like the outcome that we have. So here's one example of the the voting techniques that we were using. So the different ML models that we are using here is logistic regression, random forest classifier, and decision tree classifier. And since these are classification models, you can see that the parameter voting is defined to hard. And by hard, it means that it is going to do a majority voting technique and then give me an output. If the voting would have been defined to soft, that is primarily the case of regression models, it would have been an averaging out of the result that would have been given to me. So, yeah. Again, here we see that there's a bit difference between the training and the testing accuracy. So, yeah. Coming to the comparison of all of them, all the techniques that we discussed so far. So, as we saw, right, in the case of bagging, it was the same model. So, different versions of the same model that was being trained upon the different subsets that had been created. And all of them were parallelly, independently training on each of the subset and giving the, basically giving the output. And here it was primarily focused on reducing the variance, reducing the error rate in the testing data set. And here also averaging was done in case of regression model, whereas voting was done for the classification models. And it is primarily like the strength of this particular model was reducing the overfitting. In case of boosting, again, it was the same model, but what was happening that we were, each time there was basically there was a sequential correcting that was done in each of the training of the model. And here we were focused primarily on reducing the bias as well as the variance. And then, so what was happening was that the weighted sum of those models was being used, and this particular technique is very useful in case of handling difficult cases, and it tends to improve the accuracy much better. Like in my experience, I found boosting to do wonders for me. In case like I found this one the best amongst all the ensemble techniques. In case of stacking, it was different models. However, it was and initial set of models was basically parallelly training, and the final model was basically stacked upon the meta model was basically stacked upon this. Um, and here our main focus was combine the models in a stacked manner and gain uh, the collective intelligence of each of the models and finally get an output. And in case of Votin, again, it was a number of ML models being used, and they were independently parallelly training and giving a diverse prediction, a generalized prediction basically. And here also, the uh, output that we were getting was either by majority voting and or either by getting average. Now, there can be like a confusion that, if I have bagging, why use voting? So one simple thing here is that in bagging, what happens is that we are using one single model. It's one single model, different versions of a single model. In voting, I use a number of models. I can use different models, not just one single model and its different versions. So this was basically the comparison. So as initially I told you that I was struggling with logistic regression, basically single models. Here's one snippet, like the code snippet of the same, wherein you can see that I was not getting the desired accuracy. I was getting only 64%. And after using ensemble learning, I saw that there was a drastic change. I finally came to 88%. And as I said before, for me, boosting was the one that was my favorite. That actually gave me, like, there was much less difference between the testing as well as in the training accuracy. And yeah, so thank you everyone. Um, you can catch me up with me on LinkedIn or Twitter, and I have also attached link to the notebook wherein I have used each of these techniques. So
Thank you so much, Shaswi.